What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 8, Section 2, Graphs of the Other Trigonometric Functions. Let's do it. So this one says, explain how the graph of sine can be used to graph cosecant, okay? And remember, sine and cosecant are inverses of each other. And so this is very important. So let's say we've got it mapped out like this. Let's call this 1, let's call this -1. If we were to graph sine, okay, we'd go to the high at pi halves, then back to the middle, low at 3 pi halves, then here. So here's my graph of sine of x. Now to graph cosecant x, what I'm going to do is I'm going to take every point that's a max, okay? And I'm going to draw a little parabola going up. And this parabola, however, is going to be bounded. It's not going to go off to the left and to the right forever. It's going to be bounded. So I'm going to kind of do it like this. So these boundaries are going to occur in all these points. And notice it's not a coincidence that the boundaries are occurring when the function value is 0. That makes sense because the reciprocal of 0 is undefined. So that's why we have these boundaries, okay? And then now we get that, and then we also take our minimums. Here I've only drawn 1, but take a minimum, and then we make a parabola going down, again bounded by those same boundaries. So you can see that cosecant of x is what's graphed in red. So that's how you use sine to create it. That's it, done. So the way I'm going to show that tangent x has a period of pi is by using the unit circle. So what we're going to do is we're going to remember that tangent is equal to y value over the x value on the unit circle. So it's the y coordinates over the x coordinates, right? So I'm going to write out what tangent of these 3 values are here and then tangent of these 3 as well. So I've gotten these 6 values by dividing the y by the x in all cases, right? So you can see like this. Now when I do it down here, you're going to see that everything's going to be a repeat of quadrant 1. So watch this, right? So now I have 7 pi 6. That's why these are both red, right? You'll see they match up. So 7 pi 6, -1/2 over -√3/2. It's the same as this. It's the negatives are going to cancel out. So again, it's going to be red 3/3. And then over here, it's going to be the same thing over the same thing. Both negative, they cancel out. So 1. So you see it repeats again. And then here we have negative divided by negative, red 3/2 divided by 1/2. Negatives cancel out. It becomes red 3. So you see how it repeats. And the same will continue over here. So this down here is going to be negative red 3, which is a repetition of this. Again, they're both green. Then here we're going to get -1, and then here we're going to get negative red 3/3. So you see the repetition every pi or every 180, it's repeating. It's repeating, you see? So that's how you can show that the period of tangent is equal to pi. Done. The period of cosecant of x compares with sine of x in that they're the exact same. They repeat every 2 pi. So they're inverses of each other. They have the same period, just like cosine and secant or tangent and cotangent, they all have the same period. So they have the same period of 2 pi, boom, done. So here we're going to kind of go through each one of these. And the thing is about tangent of x, typically tangent of x, it goes right through the origin because tangent of 0 is 0. And then it goes up to the right and down to the left. And it's got a period of pi, which means it goes from negative pi halves to pi halves out here. Well, that's this one. That's this one, right? That's figure 1. So figure 1 is our tangent. Now when we come to, let's actually go to cosecant next. So cosecant, as we mentioned in a previous problem, this is for number 8. Again, we take our sine function and then we kind of draw these little parabolas going up and going down. So sine, remember, starts at the origin. So this first parabola going up will be at pi halves, okay? Well, look, this is 2 pi, this is pi, this is pi halves. This is going up. This is going down, which means that figure 2 is our cosecant. And the other one that's like this is figure 4. So these two have to be cosecant or secant. And notice that this one has a parabola kind of starting here, right on the y-axis. That makes sense because cosine is maxed out at the y-axis, right? And then it kind of comes down like this and then goes back up. And then you have another one right there. So it makes sense that, therefore, 4 is secant, aka the inverse of cosine. Last but not least, we have cotangent, which looks very similar to tangent going up, except it's reversed like this, coming down, and it doesn't go through the origin, right? So, but here again, the period is pi, so you will actually have asymptotes here and here, and then that sort of repeats like boom, boom, etc., etc. But anyways, 3 is cotangent. So that's how you do these 4. That's how you analyze them. Done. So here we're meant to find the period and the horizontal shift. So to find the period, I always say period equals 2 pi divided by b. Now this is for secant, cosine, sine, and cosecant that start with the period of 2 pi, okay? And here my b value is this term, it's pi over 4. So period equals 2 pi divided by pi over 4. Dividing by pi over 4 is the same as multiplying by 4 over pi, cancel, cancel. And the period is 2 times 4, so the period is 8. And then what about the horizontal shift? So that's in here, right? And so the horizontal shift is literally that value. So we can say horizontal shift of -1, or sometimes I say when it's plus, right? It's to the left by 1. So you could say either or, they both mean the same thing. That's how you do it, done. So this question is asking if tangent of x equals -1.5, what is tangent of negative x? So it comes down to the symmetry properties of tangent, which state that tangent of negative theta, or x in this case, is equal to negative tangent of x. So if tangent of x is -1.5, negative tangent of x is positive 1.5, which means tangent of negative x is equal to positive 1.5, boom, done. Now for this one, we're talking about cosecant, and by the way, cosecant has the same symmetry properties as sine, and for sine of negative x, it equals negative sine of x, which means that cosecant of negative x is equal to negative cosecant of x. So they're saying that cosecant of x is -5, so to negate that, it becomes positive 5. That's how you do it, done. So for this one, they want us to rewrite everything so that the argument, aka x, is positive. So since the symmetry property of tangent and cotangent is that, it's just odd, right? Which means cotangent of a negative is the same as negative cotangent of that positive. The negative is going to come out front. So it's the same as negative cotangent of x. And then cosine of negative x, cosine's even. So cosine of negative x is the same as cosine of x. So I can just replace it with cosine of x. And then sine of negative x, again, it's odd. So sine of negative x is equal to negative sine of x. So now all the arguments are just positive x, you can see, right? And so this is the final form. That's how you do it, done. Okay, so for this one, we're going to start by factoring the 4 out before we graph anything. So we got 2 tangent, and then we got 4, and then we got x minus 8, right? Because I'm dividing this by 4. So what this means is we have a stretch factor of 2. That would be like an amplitude. Otherwise, we got a stretch factor of 2. Normally, the period of tangent is pi, but then we're dividing by that value. So the new period is pi fourths. And then we also have this right here, the -8, which is normally like a horizontal shift to the right, but it's a horizontal shift by 8. That's a lot. That's like way more than this period. So we got to figure out sort of, where a nice center point would be. So normally we would start right here at the origin, and tangent kind of goes up to the right and down to the left, something like this, right? But now this has been shifted 8 units to the right. So what I'm going to do is I'm going to take 8 and I'm going to subtract multiples of pi fourths in the calculator until I get one that's between 0 and pi fourths for my first starting point. So you see, once I subtract 10 multiples of pi fourths, I get something that's less than pi fourths. I get about 0.146. So now if I label this as pi eighths, half of pi fourths, and this is negative pi eighths, this is a distance of pi fourths right here, right? Pi eighths, another pi eighths, it's pi fourths. And again, if pi eighths is 0.3926, this is 0.14. This is about a third. So 1, 2, 3. So I'd say like maybe we're right here for that starting point. And then now we can get the asymptotes, right? So normally the asymptotes would be here and here, but here's the center. So the asymptotes are a half period to the right, half period to the left. And so now normally, right, if we had 1 and we had 2, we have -1, -2. Normally, when we go halfway to the asymptote, like here, we'd be at 1, and then you'd kind of curve it up. But there was a stretch factor of 2. So instead of coming to this halfway point and going up only 1, we're going to go up 2 now. Same with this. So you see it kind of like stretches it out a little bit, and then we can kind of connect the dots. So now to get an equation for all of these vertical asymptotes where, k is going to be an integer, okay, k is going to be some integer, we can start by saying normally the asymptote is at pi over 2, okay, right? It's at pi over 2 and then multiples of pi. So pi over 2, 3 pi over 2, negative pi over 2, adding and subtracting by pi. So we're adding and subtracting by multiples of pi. That's why we put the k value. That's any whole number integer, right? And then just like with the period, just like how we divided by 4, we have to divide these by 4, aka multiply by 1/4, right? And then the last thing we did was we did a shift, and we saw that this shifted, okay? And because it shifted 8 units to the right, that phase shift, we have to add 8 here. So that's how you do it. Boom, done. So before I start this one, I'm going to factor out pi thirds from that inside argument. So we get pi thirds, and then I get x plus 3, right? Because when I redistribute it here, I'll get just regular pi like we have here. So now we see we have a stretching factor of 6. We also have a period. Since cosecant typically has a period of 2 pi, we divide by this value here to get the new period. So 2 pi divided by pi thirds is the same as 2 pi times 3 over pi. Pi's cancel out. We get a period of 6. And then we get a horizontal shift of 3 to the left. So this is great. And my strategy for these is usually, since this is cosecant, I'm going to graph the sine function of this. I'm going to graph this as if it were sine, and then we're going to use that to graph the cosecant. So sine, in this case, since we have a period of 6, I'm going to literally go by 1, 1, 1, 1. So this is 6 right here. This is -6 here, okay? So there's 2 periods. And then we're shifting. So normally we would start here for sine, but we're shifting 3 to the left. And this is nice because that's a nice whole number. So we just go 1, 2, 3. And by the way, the stretch factor is 6. So I'm going to call this 6, and I'm going to call this -6. So we're going by 2's, right? This is 4, this is 2, this is -4, this is -2. So now from this point, we can start to map out the sine function. So we know we have a period of 6. So this is -3 going to 3. And we can see within that time, it's going to do our whole thing. It's going to go up, down, up, right? But let's map this out, right? So first it goes up. So the first period, so this is the period, this is a half period, this is a quarter of the period. This is where it goes to that max of 6. And then it's going to come back down to 0. And then we're going to come back down to the minimum at -6 and then up, right? And then again, it's going to continue on up, back to the middle. And then we're going to do the same to the left, right? We're going to go down and then back up to the center line. So it's 2 periods. Let's connect the dots. So this is really great because the first thing I can do now is I can graph the asymptotes, and that's for all the x-intercepts. And then now is the fun part. Now we just create the little mini parabolas that are inside these constraints, right? So here at the mins, we're going to graph them going down. And here at the maxes, we're going to graph them going up. And these asymptotes are easy, right? Because they're all multiples of 3, 0, 3, 6, etc. So we can just literally say for the asymptotes, x equals 3k, where k is an integer, you know, it's any integer, right? 0, 1, 2, 3, -3, -2, whatever we want, okay? So there is your answer, boom, done. So this one is pretty much a typical tangent function, except for a horizontal shift to the right by pi halves. So since we normally have tangent being centered right at the origin, all we're going to do is we're going to shift it by pi halves. And by the way, I'm going to call this pi halves. I'm going to call this pi. And if you remember, tangent has a period of pi. And this is great because all I'm going to do is take that center point that's normally right on the origin and shift it over. And then I'm going to take my asymptotes, which are normally at -pi halves, and shift that to the right by pi halves, which will be right here. And since the period is still pi, I'm just going to have the period repeat with these nice asymptotes. And now we do our typical tangent graph, right? Starting here, and we got a point here, 1 up and -1 down right here. And that's halfway between this center point and the asymptote. And then we connect the dots, and then we continue on up. And then we also go here and bring it down, and we repeat. And the asymptotes are just on multiples of pi. So x equals pi k, where k is any integer, okay? And there are the asymptotes. So, and by the way, the period wasn't modified, so the period stays as pi. The stretching factor, since there wasn't a constant, it's just 1. And that is pretty much how you do it. Boom, done. So this one is a typical tangent function with the exception of a horizontal shift. And that's a horizontal shift to the left by pi fourths because it says plus. If it said minus, it go to the right. Everything else is kind of standard, right? Which means the period is the standard period, which is 1 pi. The stretching factor is just 1 because that's our coefficient, right? It's an invisible 1. So what I like to start with tangent is to recognize that we usually start at the origin, and we usually have asymptotes at pi halves, and -pi halves. Those continue out, you know, periods of pi, right? And then we go like this and like this. But what we've done is we're starting with this shift to the left. So instead of being here, if this is pi halves, this is pi fourths, right? Half of pi halves. So I'm shifting to the left, boom. So likewise, my asymptotes shift to the left. So instead of being at negative pi halves, they're here. And my other one is here, and so on and so forth. Okay, now since nothing else has changed, I'm going to plot the points. Remember, we go up 1. Let's say this is 1, right? And then we go up 1, and then we kind of follow up the asymptote, hug that asymptote. Likewise, we come down the other way, and then let's complete for the rest of the periods. And last but not least, I can say that the vertical asymptotes are at x equals, that looks like pi fourths. I can choose a random one, so I'll just take that one, x equals pi fourths, and then it's plus pi k. It's in periods of pi. So we multiply by multiples of pi where k is any integer. So that's the asymptotes, that's the answer, done. So for this one, we're going to start by graphing the inverse of cosecant, which is sine. And we're going to take a couple things, right? We know that the amplitude is 2, but everything else is unmodified, which means the period is our standard 2 pi. Amplitude, we've been calling it a stretch in other problems, but you know, for sine and cosine, it's amplitude. But if we want to say stretching factor, we'll just call it the stretching factor, okay? So we'll call that 2. And since there's no vertical shift, we know we have a center line at 0. So let's start putting this stuff in. And we know for sine, we're typically starting in the origin, so that's going to remain the same. And then we go up to the max at pi halves, down back to the center line, down here, and then up, right? We follow that wave. Same thing. We go down, up, down. Now let's connect the dots. Now again, this is sine. We need to graph cosecant, okay? So cosecant, first we're going to start with the asymptotes. And the asymptotes are where all these nice x-intercepts are. So let's plot those. So those are the vertical asymptotes. And then now the last part, the fun part, we hit the maxes and the mins. So at the max, we take a nice little parabola bounded by those asymptotes, of course, going up like this. And then at the minimums, we go down the same way. So again, what's in red, that's the function. That's cosecant. And these asymptotes are just occurring at multiples of pi, 2 pi, negative 2 pi. So we could just say pi k, where k is any integer. So that's how you do it. Boom, done. So for this one, we're graphing secant. So I'm going to start by graphing the cosine function, okay, because it has a relationship with cosine. So we're going to start there. So let's imagine 4 cosine of 3x. So for 4 cosine, we can say that the stretching factor is 4, but that's also the amplitude, okay? So the amplitude of cosine is 4. And then we got this 3 multiplying the x. That affects the period. So the period is normally 2 pi. Now it's 2 pi divided by that value, which is 3. So the period is 2 pi thirds. So now we got enough information to graph this cosine function. So let's do that now. And again, there's no vertical shift, so our center line goes right on the x-axis. And we know we got an amplitude of 4. So I'm going to make this 4. That's the beauty of not having any markings. I can kind of choose how I want this to look. So I got 4 and negative 4. So the function is going to go like this in between those. And then now we have a period of 2 pi thirds. Again, there's no horizontal shift, nothing, no vertical shift. So normally cosine starts at the max. So we're going to start at the max here. And then the period is 2 pi thirds. And I'm going to arbitrarily just say that this is 2 pi thirds, okay? And then another 2 pi thirds would be 4 pi thirds, and we'll go the other way in the negatives. So now this makes it really easy to graph this cosine function, right? So a period is 2 pi thirds, so it's going to go back to those max points at all these spots. It's going to go down to the minimum in between these points. And then in between the max and the min, it's going to hit that center line. Boom. And now we connect the dots, so we get this nice little curve. And now that we graph cosine, we're ready to graph secant, because first, we can start with our vertical asymptotes. That's at every x-intercept. So let's graph those now. And there are the asymptotes. And now at every max, we kind of make an upward parabola bounded by these asymptotes. And same thing at the minimums, except for now these are going down. And then if you look at the increments of each of these are each pi 6, right? And then for the asymptotes, we have one occurring here at pi 6. And then they're occurring every pi thirds from pi 6, right? Here is one occurring at 3 pi 6, 5 pi 6, etc. So we're adding on by pi thirds k, where k is an integer. So that's how you do it. Boom, done. So for this one, since we're graphing secant, I'm going to actually graph cosine. So I'm going to graph 7 cosine of 5x, and then we're going to use that to graph secant. So first of all, we have this stretch factor for the original of 7, which means that the amplitude of cosine is actually going to be 7. We also have a modified period. We divide the typical period of 2 pi by this coefficient of 5. So the new period is now 2 pi divided by 5. So now we have enough to get started. Let's draw that nice center line. There's no vertical or horizontal shift, so the center line's right on the x-axis. And just to make this not look so crazy, I'm just going to arbitrarily say that this is 7 and this is -7 because that's the amplitude, that's the max and the min. And because we're talking about cosine, and there's no vertical or horizontal shifts, we know that we start at the height. So on the y-axis, we're going to start at that high point. Now, since the period is 2 pi fifths, I'm just going to make this be 2 pi fifths, and I'll make this be 4 pi fifths, and so on and so forth. So since the period repeats every 2 pi fifths, we're going to go again to the max here, 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 and here. Our minimums are going to be in between these guys, so down here, in between these two, down here, in between these two, here and here. And then in between the max and the min, we're hitting that center line like this, boom. And now we'll connect the dots. Now that we've got this, we can build in the asymptotes, the vertical asymptotes of our secant function, and that's gonna exist at every x-intercept. And then now let's graph the actual secant function within these asymptotes. So again, every max I'm gonna take and I'm going to draw up like so. So you see we have these nice little parabolas going up, fitting in between these asymptotes. And then we're gonna take all the mins and we're gonna draw parabolas going down. And for the asymptotes, this one right here is occurring at pi tenths. So the way they have it in the back of the book is they have pi tenths times k, where k is any odd integer. And that's cool if you want to specify that, but sometimes teachers want just k to be any integer. So what we can look at is we can look at this distance here between each asymptote. It's the same, it's consistent. So if the full distance is 2 pi fifths, it's half of that, which is 1 pi fifth. So I could also say plus k times pi fifths times increments of pi fifths, where k is an integer. So this is a slightly different way to write it. I think a little bit more universally accepted, but again, you could also put k here and say the integer is odd. It will do the same thing. So that's how you do it. Boom, done. This one is cosecant. So first I'm going to turn it into sine, and then I'm going to graph that. We'll use that to graph cosecant. So we got a stretching factor of 2, and also that's going to be for the sine function, that's going to be an amplitude of 2. We've also got a shift to the left. That's a horizontal shift to the left by pi fourths. And last but not least, we have a vertical shift down by 1 because of that -1. So let's plot all this stuff out. So first we have our center line occurring here at -1. That's the vertical shift down for -1. Then we have an amplitude of 2. That means we're going to go up to +1 down to -3. And again, since we're starting with sine, normally we'd start here, but there's a shift, and the shift is going left by pi fourths. And by the way, the period is unmodified. So the period is just still regular 2 pi. So we'll make this pi, we'll make this 2 pi, we'll make this -pi and -2 pi. So there's nice 2 full periods. And again, normally we'd start here, but we're shifted to the left by pi fourths. So now our starting point is going to be shifted 1 spot back, and now we can begin. So we know that the center line is going to repeat every period. The period is 2 pi. So here's 1 pi, here's 2 pi. And it also kind of repeats in the middle here. And then we kind of go up with sine, right? So we go up, up. So first, halfway between these points, we're up. Then we come back here. Then we go down, halfway in between like this. And then as we continue this out, we're going to, again, go down here, then back up to the center line, then back up to the max, and then back down like so. Now we're going to connect the dots. So now that we have this nicely plotted out, now we can start to graph the cosecant function. So the first thing is, normally we look at the x-intercepts for the asymptotes, but here we look at where we intersect this center line, this midline. So I'm going to put in these vertical asymptotes. And then now as we graph the function, we do little upwards facing parabolas here from the maxes, and then downward facing parabolas from the minimums, again, staying within the asymptotes, right? So these nice little mini parabolas that stay within those lines. And last but not least, we need our asymptotes. So the asymptotes, we could say that we have one here at -pi fourths, and then it's repeating every pi. So I could say plus pi times k, where k is an integer. So that's it. That's how you do it. Boom, done. So for this one, we're graphing cosecant. So I'm going to start by graphing sine. Okay, so we'll say we have 7/5 sine of x minus pi fourths. Now there's two things happening. Number one, we have a coefficient here which will affect the amplitude of sine. We can also call it a stretching factor of 7/5. And then we have a horizontal shift. And this horizontal shift is going to the right by pi over 4. Nothing else is being changed. It's not being vertically shifted. The period's not changing, so the period is our standard 2 pi. So now we have enough information, we can start plotting this out. So since there's no vertical shifts, we have that nice center line or midline right on the x-axis, and then we have a period of 2 pi, so I'll just make this pi, and I'll make this 2 pi. And because it's sine, we're normally starting here, but we've now shifted to the right by pi fourths. This is pi fourths, this distance, so now we're starting here. Last but not least, it says the amplitude is 7/5, and so since I can make this whatever scale I want, I can make this 7/5 and make this -7/5, just to make it look nice. So why not, right? Okay, now we see that the period is 2 pi, so this would be 1 pi, 2 pi, so we're gonna return back to this center line over here after one period away, and we're gonna hit the center line in the middle as well. Now, as we go up, so kind of in the middle, right, we're going up first. And why? Because we always go up first with sine unless there's a modification. So we go up to that max, back down, down to the min, back up. And same over here, but we go in the reverse direction, down to the min, up to the center, up to the max, down to the min. So it kind of follows that pattern. Now let's connect the dots. So now that we got this great sine function mapped out, now we can plug in the vertical asymptotes. It's wherever we're hitting that center line or the x-intercept. So let's do that now. And then now that we got those, let's graph little parabolas starting at the max first, like this. And then at the minimums, parabolas going down like this. Again, all of these are staying within those vertical asymptotes. And the equation for the vertical asymptotes are going to be, well, I see one there at pi fourths, and then it's repeating every pi. So I can say plus pi k, where k is any integer. So that is how you do it. Boom, done. So for this one, we are meant to graph this tangent curve when we got the center at pi fourths 2, and we basically got no stretching factor of 1, and then a period of pi thirds. So let's see how we can put this together. So we've broken it up into pi twelfths, okay? And the reason why is because 2 pi twelfths is pi 6, 3 pi twelfths is pi fourths, okay? So this value right here is pi fourths, and that gives us our center right here at pi fourths 2. Now it says the period is pi thirds, which means I'm going to go pi 6 to the right. And why am I going 2 spaces away? Because pi 12, that's a pi 6, right? And then I'm going to go pi 6 to the left as well. So now we kind of have our vertical asymptotes as such. And then now with this a value equaling 1, I just kind of go up 1, down 1 as I go halfway between this point and the asymptote. And I'll do the same here. Boom, boom. And now we'll connect the dots. And I know this is good to go because tangent usually goes up to the right. So this is following that standard procedure. And now if we want to get this together in an equation, we'd say a value is 1. So I got nothing in front. And then the period is normally pi, so it's pi thirds now. So whatever the b value is, we divide pi by that. So the b value has to be 3. And then it looks like we've shifted to the right by pi fourths, right? Because normally the center is at 0. So we're going to minus pi fourths like that. That's shifting to the right. And then last but not least, we've moved it up from the x-axis to 2. So then we're adding a 2 for a vertical shift up. So that's how you do it. Done. So for this one, I'm actually going to kind of graph the function, like either whether it's sine or cosine first, hitting my max here, my x-intercepts or midpoints there, and like this. So let's first do that. So this is starting at the origin. It's starting up. This sure looks like sine. And instead of a period of 2 pi, which is normal, it has a period of pi, right? It's cycling in that one period. So normally it'd just be sine of x, but then the period is cut in half. So I'd actually put a multiplier of 2 next to the x. That's the b value. So this would be sine of 2x. So if this is sine of 2x, then since this is the sort of inverse of that, right, it's going to be cosecant of 2x. So it's the exact same. We just switched from sine to cosecant. That's how you do it. Done. So for this one, I'm going to start by plotting in the main graph here by connecting these mins and maxes. So to me, it's going through the origin, it's going up to the right. This looks like your classic sine function. The only thing that's changed, the amplitude is still 1. The only thing that's changed is the period. So the period is pi over 2. Now, normally sine of x would have a period of 2 pi. To get a period of pi over 2, we'd have to divide this by 4, which means that's the b value that goes in front of the x. So then it would be sine of 4x. And so since we're taking the inverse, we want, whatever is going to create those, that's going to be the inverse of sine, which is cosecant. Hence the answer is cosecant 4x, boom, done. So for this one, I'm going to start by connecting the dots between these mins and maxes. So to me, this looks like your typical sine function, right? Starting at the origin, going up, down, etc., with the correct normal period, I should say, unmodified period of 2 pi. The only thing that's different is the amplitude. The amplitude is 2 instead of your standard 1. So instead of sine of x, it'd be 2 sine of x. But since we want the inverse, right? Because we actually want this function. So now I know we're working with sine, so I just switch that to cosecant, keep the 2, and there's your f of x, boom, done. So this one kind of looks like a typical tangent function, right? It's going through the origin, and then it's going up to the right, down to the left. I'd say there's a couple interesting things to note. Number one, we see that it's not going up to 1 halfway between this point and the asymptote. If it was, then we'd have our standard sort of amplitude, but it looks like the amplitude's been cut in half. So I'm going to start by saying it's 1/2 tangent. Now, the other thing is the period is normally pi. It normally goes from negative pi halves to pi halves, but look at this. It's such a much smaller period. It's going from negative 0.005 to 0.005, which means it's a period of 0.01. So usually what I say is then we need a b term, right? Pi divided by b is equal to this period, which is 0.01, which means if I swap these guys, multiply by b, divide by 0.01, divided by 0.01 is like multiplying by 100. So b is 100 pi. So inside, we're going to have 100 pi x like so. There is your f of x, boom, done. So for this one, we're meant to use a graphing calculator to look at the graph, so let's do that now in Desmos. So here's absolute value of cotangent of x, and it's pretty cool because normally you'd expect the function for regular cotangent without the absolute value to go down here, but it makes sense that it looks like this because when you put an absolute value, all the negative values are now flipped up and made positive, so that's what it looks like. So for this one, it says to go ahead and graph it in a graphing calculator, so we'll do that now, but I do want to point something out to you. Cosecant x is really 1 over sine of x. Secant x is really 1 over cosine of x, which means it's really, because it's in the denominator, it's really cosine of x over 1, which means this simplifies to cosine over sine of x, which is the same as cotangent of x. So this function should look like cotangent of x when we graph it in Desmos. Let's take a look now. And check it out. That looks exactly like a typical cotangent function, right? From a period of pi, negative pi to 0, up to the left, down to the right. So there you go, boom, done. So for this one, we're meant to graph it in a graphing calculator, so let's do that now. So here's the graph, and you can see a couple different periods, 2 different periods. And the main idea is, look, you see this multiplier. When you take your normal period of secant, which is 2 pi, to get the period of this function, you're dividing by 0.001, which is like multiplying by 1,000. That's why the period is now 2,000 pi instead of 2 pi. So that's how you do it, done. So for this one, they want us to graph it in Desmos, but I'll show you something interesting. This is actually an identity, and sine squared x plus cosine squared x actually equals 1. So when we graph it, we should see just a horizontal line at y equals 1. So check it out, sine squared x plus cosine squared x, it's that line right at 1. You see, it's always equal to 1 because that's an identity. So that's what it looks like, done. Standing on the shore of a lake, a fisherman sights a boat far in the distance to his left. Let x measured in radians be the angle formed by the line of sight to the ship and a line due north from his position. Assume due north is 0 and x is measured negative to the left and positive to the right. Okay, standard. And the boat travels from due west to due east, ignoring the curvature of the earth. And the distance in kilometers from the fisherman to the boat is given by this function. So it's a trig function. So here's a quick little graph, right? Here's the fisherman, here's the boat, and here's due north. So here's the angle x. So it says, what's a reasonable domain? Now, the thing is, the boat is going west to east. So it's starting here and it's kind of going this way. And the fisherman's just chilling. So you imagine as it comes to the other side, it's going to go this way, this way, this way. Now, even if the boat is really, really far to the left, right? Let's say over here, even like this, that x value, you can tell, like, even if it's over here, the angle's never going to get beyond 90 degrees. And they're saying it's negative going this way, so negative 90. But in radians, that would be negative pi halves. And then as the boat goes to the right, now we're talking about positive angles, but even as it goes further and further, it's never going to go beyond 90. So again, in radians, that's pi halves. So I'd say A reasonable domain would be from negative pi halves to pi halves, not including those values, but up to those values, so hence the curved parentheses. Now we need to graph this on the domain, so let's go ahead and do that in Desmos. So here is the graph, right? Just like what we'd expect from secant, cosine the max would be here, and then we just kind of go up with that parabola. And there are the vertical asymptotes, and the vertical asymptotes I actually drew in. They're occurring at pi halves and negative pi halves. That makes sense. That's our domain, okay? So when we talk about the vertical asymptotes here, they're just the boundaries for what are acceptable angle values or what angle values we can actually get here. And the other thing to note is as we approach these asymptotes, as we get to 90 degrees or negative 90 degrees, in our case pi halves or negative pi halves in radian, you can see that the distance goes off the charts. It approaches infinity. So that's kind of what it represents as well. Now to calculate the function value at negative pi thirds, we're going to plug it into Desmos. So here we get an answer of 3. So what that means is when the angle is at negative pi thirds, the distance of the boat to the fisherman is 3 kilometers, because it did say it's measured in kilometers over here. Now let's do d of pi 6. Let's do that in Desmos as well. So here rounded to the nearest hundredth is 1.73. So we can say when x equals an angle of pi 6, that would be like somewhere over here. The distance would be 1.73 kilometers, okay? And then now we get to F. What is the minimum distance between the fisherman and the boat? When does this occur? So I think we remember from the graph that occurs when x equals 0. That's when it's right due north, okay? When the angle is 0 radians. And now let's find the minimum on the graph. And it's right here. It's a distance of 1.5 kilometers. So the minimum distance is 1.5 kilometers. And that's how you do it. Boom, done. A video camera is focused on a rocket on a launching pad 2 miles from the camera. The angle of elevation from the ground to the rocket after X seconds is this. So here's my little diagram representing everything, right? We have the camera here, we have the launching pad here, we have the rocket here. It's sort of like mid-flight. And then this angle in here is pi over 120 times X, okay? And we're trying to first get a function representing this, the height, okay? So let's think about our trig functions, because I did put this right angle in here because this is a right triangle and that's important. And we're going to remember SOHCAHTOA. So I want this. This is a leg of the triangle. And I know this is another leg. So the function that uses 2 legs is tangent. Tangent of an angle equals opposite over adjacent. So let's start with that. So we got tangent of pi over 120 times x equals opposite over adjacent, multiply both sides by 2, and there's our function. We get h, we could say h of x actually equals 2 tangent of pi over 120x, like so. Now to graph this on the interval from 0 to 60, let's do that in Desmos. So here's what the graph looks like. It kind of goes up to the right like so. And now we want to evaluate h of 0 and h of 30. So again, let's do that in Desmos. So h of 0 gives a value of 0. H of 30 gives a value of 2. So this basically means when the angle is 0, that means the height is 0. When the angle is 30, or the angle is 30 pi over 120, which is really pi fourths, the height is 2, and this is in miles, right? That's what the height is in, because that's what this is in as well. And by the way, these values are in seconds. So this is at 0 seconds. This is at 30 seconds. And then last we get to D. What happens to the value of h of x as x approaches 60 seconds? So when we go back to the graph, we see here that at x equals 60, that's basically like our little vertical asymptote, which means this is actually never going to hit 60. Okay, but it's definitely approaching infinity as we get closer and closer to 60, right? It's going up and up and up. So, what could this mean? This could mean a number of things. This means that like, hey, something weird is happening at 60 seconds. One possible explanation is that maybe the camera can no longer track it after 60 seconds. So this function doesn't accurately model what happens exactly at 60 seconds, but it sure looks like it's going really, really high. So anyways, that's how you do it. Done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.